And this is live. Hello, everyone. Today is November 17th, and this is episode 24 of All Things DOCSIS. I'm Brady Volpe, founder of Volpe Found and member of this. Today, we have a great episode for you on DOCSIS 3.1. We have some great guests with us. We have John Downey, CMTS technical leader at Cisco. John, welcome back.
Good to be back, as usual.
Also is Jeff Riddle, Solutions Architect at Cisco Systems. Jeff, good to have you on.
Hey, everybody.
And
there you go. Is it on now?
Technical difficulties there. And last but not least is Jason Miller, Technical Marketing Engineer at Cisco Systems. Jason, welcome.
Thanks, Brady.
Also is Jeff Riddle.
Oh, okay.
You guys hear me?
Hold on one second here. We have you on.
Is your mic turned off, Jeff?
Yeah, that comes to us.
And last but not least, Jason Miller, Technical Marketing Engineer. I think I have a technical system going on here. It's crazy here.
Okay.
We'll just talk amongst ourselves.
Yeah. I'm not sure where it's coming from.
Okay.
One second here.
All right.
Okay,
So,
we got that taken care of.
All right. You good? Are you good?
Yeah, we're all good. So
We have three of us in the same room, but on three different PCs. So we have to kind of manipulate our microphone and speakers as we go back and forth. So Jeff, Jason, and I are all in Research Triangle Park, Raleigh-Durham area. So Cisco has a 12-building campus here. And we're all gathered together to do some testing and troubleshooting this week on some DOCSIS 3.1 stuff. So that's why we're all, you'll see my backdrop's different from my house. I usually have a bird in the background and dogs and grandfather clock and all kinds of other stuff going off.
Yeah. So the topic today is DOCSIS 3.1, which is why we got all you guys together. And John and Jason, I heard Cisco had a few cool demos at SCT Expo this year. You guys want to share some of that?
Yeah, I'll talk real quick and then pass it over to Jason because he was actually there. This is probably one of the first SCTs I haven't gone to in like 20 years. I just had no desire to go to Philadelphia again, and there was a lot of us stuff going on. But we pre-demoed or staged the demos in Atlanta a couple weeks before that, and we set up really for three specific demos. That was DOCSIS 3.1 Upstream to show we could do OFDM and how far we are along. We showed DOCSIS 3.1 Downstream as usual, but it's nothing new there anymore. We're deploying DOCSIS 3.1 Downstream now, so it's really not that new. But we did show two OFDM blocks, 192 megahertz apiece, with 32 single carrier qualms, all cross bonded. I believe we showed almost 5 gig across 2 modems, so 2.5 gig per modem. These new 3.1 modems only have 4 gig E ports, and you only get about 960, 970 meg per gig E port. So we were getting about, I think, 2.5 gig per modem, 2 modems, 5 gig, somewhere in that range. The other one was we did remote PHY. So to show that we are getting further along with remote PHY. So you're taking the PHY chip and putting it out in a node or a 1RU shelf. And then we also showed the virtual CMTS. So that takes remote PHY one more step where you're taking the PHY layer, moving it out, but now the CMTS is just packet processing. It could be a server. So you don't really need a CMTS anymore. So the virtual CMTS is like taking a server and putting code on it that looks like a CMTS code, and now talking through gigabit Ethernet, through a Metro Ethernet link or whatever, talking to remote PHY nodes. And that was sort of the demos we gave. I want to pass it over to Jason. He can elaborate a little bit too.
Yeah, no, I think those were the demos that we had. I think the virtual CMTS as well obviously requires the remote PHY components on it. But both the ones we were both running the remote PHY and the integrated CMTS out of our same CCAP platform where we're doing the demo as well.
Okay, Jason, you also did some DOCSIS 3.1 testing at customer sites, right? So some of this it's not just in a lab; it's actual in the real world, correct?
Right, we did. Matter of fact, I co-presented with the customer, ABNY Midco, at SCTE on our early field trials that we've done with DOCSIS 3.1.
Hey,
And how's that going? So
Wow.
what's it look like in the field?
I got someone talking about it over here. I don't know who it is.
Yeah, I'm sure you can hear me from this one too. Before we go down that route, I wanted Jason to elaborate on what speed we saw on DOCSIS 3.1 and kind of talk about that a little bit more before we go into the plan.
Yeah, on the downstream or the upstream?
Upstream.
Yeah, on the DOCSIS 3.1 upstream, on there, the modems we were using only ran to 5 to 85 megahertz. So even though we had a 96 megahertz wide channel option, I think we ran it from somewhere like 15 to 80. I think, yes, we did about 75 megahertz worth of OFDM spectrum, OFDMA spectrum. We were getting about 450 megabits per second. We run that across 2 modems when we did that.
Okay, so you're doing OFDMA in the upstream now.
We are, yeah. Well, certainly at the show we are doing it. We're doing some early stuff now, but in production deployments, DOCSIS 3.1 downstream, OFDMA is we're running that on the box now. Yes, the hardware is the same hardware that we've been having to do that, but now actually have some of the software functionality turned on.
Okay, that's actually really great to hear. So because I mean, OFDM in the downstream has been a lot more prevalent, but we're not hearing as much about OFDMA in the upstream.
Right, and that was what kind of predicated some of the testing out here in RTP is to play around with some of that in addition to some other things. What we usually do is we try to get a spreadsheet together between us to kind of figure out what's the expected speeds, and then go and kind of start doing some testing to see if we're kind of measuring up to that, and if we change these parameters, do they reflect the changes in speeds we expect? So.
Right. Okay, I understand. That's awesome to hear that's happening.
Yeah. But yes, that we are doing on the downstream, obviously, like to your point, a lot further along. So we've been doing that even in deployments out across HFC plants on there.
Right. Now, is there anything else that John wants you to cover before we can move on to customer testing in the plant?
So as I roll my chair up on you, this is how I roll. That's how I roll. I'm everywhere. Jason's done some great stuff with some of our customers in live plant. So getting some feedback in a real plant, say node +5, not node +0, not in the lab, but real fiber and real coax. So I thought it was kind of interesting, some of the and some of the manipulation you can do in DOCSIS 3.1 to get maybe different MER readings on some of your subcarriers. So he's going to go over some of that and has a few graphs to show as well. And so he can talk about that.
Yeah, so I mean, I think if we're going to talk about MER readings per subcarrier, I think we should also explain why it's important to read MER per subcarrier versus the way we've done it in the legacy, where with an SC-QAM channel that's 6 megahertz wide, reading MER on a 6 megahertz wide subcarrier is pretty easy. In a 6 megahertz chunk, we have a lot more subcarriers that we have to look at, and so that becomes computationally more difficult and more challenging for the cable operator, right? So maybe you guys can elaborate on that when you get into that part of the discussion.
Yeah, okay.
So please go ahead.
Yeah, no, I was going to say, even initially, I think some of the deployments we see, which are probably in line with everything else, which maybe people expected and maybe they didn't. Some of the things that we saw were maybe a pleasant surprise. We always were kind of thinking that if your plant could do 256 QAM, then 1024 QAM with the addition of low density parity check would enable you to do that. We were actually seeing, better performance in that. Oftentimes 2048, and on some of the shorter plant, we were seeing 4096 QAM. So that was a pleasant surprise in their deployments. And it was actually DOCSIS 3.1 was running higher order modulations than maybe what we originally expected.
So I think that's really consistent. I was at SCT Expo, and there was a morning breakfast panel we had, and we were talking about DOCSIS 3.1 deployments that primarily Comcast was doing. But they said they were seeing pretty much the same thing, actually better performance of DOCSIS 3.1 in the downstream than what they had expected.
Right.
Where they were expecting to do 1024 QAM, they were doing maybe 2048 or even 4096 QAM in the downstream. The LDPC was working that well, OFDM in the downstream was working that well. So very consistent with what you're saying.
exactly. I think one of the other things that was kind of, I wouldn't say it was an eye-opener for me, but I think for the industry that we'll have to kind of keep an eye on is when we do run low-density parity check, it is just more robust at correcting errors. It doesn't actually keep the errors from happening. So correctable FEC errors are going to be a normal course of business, where back in the DOCSIS 3.0 days, if you were seeing correctable FEC errors, that was usually a precursor to other problems, and you usually want to go out and try to address it. And now I think just seeing correctable FEC errors, as much as 100% of the code words having at least some kind of errors, is going to be a norm in DOCSIS 3.1.
So, I mean, how does that show up? We're used to seeing correctable and uncorrectable FEC on a CMTS. You know, we see that on the counters and stuff. We track that. Is it the same way with DOCSIS 3.1? Do we still see correctable and uncorrectable FEC errors or code word errors as we may see it on a system? Or is it now different?
It's still going to be code word errors. I think some of the things, you know, we're all kind of getting our together as we move more into DOCSIS 3.1. Originally, when we were doing some of our testing, maybe some of the SNMP MIBs coming back from the modem, because obviously, since it's on the downstream side, it's the modem that's going to be the one to determine whether there was correctable or uncorrectable errors. And some of those MIBs sometimes are a little off. Oftentimes, what we would have to do while we're going out and doing some of our testing was actually get into the modem either through console or telnet and get the information directly off the modem as far as we would see the total blocks that were sent, code words, and then how many were errored, or how many had correctable errors, and then how many had uncorrectable errors. And even though we saw very high correctable error counts, we saw next to no uncorrectable errors.
This is on DOCSIS 3.1.
DOCSIS 3.1. Yeah, exactly.
Okay. So, I mean, it's still going to be kind of apples to apples, or it's going to be a similar scenario. Just we're going to see a lot more errors than what we were used to seeing before.
I think the point that that Jason's trying to make is, you know, with DOCSIS 2.0 and 3.0, we would always see correctable, and eventually it would lead to uncorrectable. And we would always say, you know what, 5%, 10% correctable eventually is going to probably lead into 1% uncorrectable, or at some point, right? I think because of the low density parity check and how 3.1 works, we're not sure yet. I mean, this is part of the growing, right? Learning as we do this stuff and best practices. We're seeing more correctable, but not uncorrectable. Like, I can't say 30% correctable, the sky is falling, is going to lead to uncorrectable, because with 3.1, maybe I will see a higher percentage of correctable, but I don't have to act on it like I would for 3.0 or 2.0. And that's what we're trying to get our heads wrapped around a little bit, is we might inherently see higher correctable FEC because a couple blips here and there, but that's not a reason for us to start ripping everything apart or saying the plan is bad. You know, the sky is falling. So it could be SNMP, it could be cosmetic, it could be just the way it is. It is what it is, and that's what we're getting at, I believe. You know, I'm going to go back to Jason.
Okay. So what's the deployment look like now? I mean, are we seeing lots of paying customers deploying this equipment at this point, or are we still mostly demoing and stuff?
Yeah. So certainly in their case, most of what they were doing was still friendlies, employees. A lot of that really just stemmed out of the fact they were having some issues just getting their hands on cable modems, DOCSIS 3.1 cable modems. So you can't really have a big deployment when really all you get your hands on is maybe 20 cable modems for some testing. So that was kind of their initial things. I think recently they've just gotten some more cable modems in, maybe like a couple hundred, so where they could start doing more of a production deployment, paying customers.
Okay. And how about like what frequency bands are operators deploying DOCSIS 3.1? I would say both in the downstream and even in the upstream.
Yeah, obviously on the customer wise, on the everything's been on the upstream side. Let me see. I was going to show you some of the graphics that we might have had to run.
Let me pass over to me for a second.
Yep.
All right. So it's interesting, you know, on the upstream, we don't really have much spectrum to deal with anyway. There's only like 2 systems I deal with that are 5 to 85 megahertz, and none of them are in the U.S. So there might be a couple looking at 5 to 85 megahertz. And then obviously DOCSIS 3.1 spec goes a 204-254 split, but I think by the time we even think about a 204-254 split, we'll start looking into FDX, you know, full duplex. full duplex DOCSIS, where we don't really have diplex filters, but now we're talking about node plus 0 probably. So that's further down the road, just to get more upstream speed. With downstream, that's sort of where I'm leading in the downstream spectrum analysis. If you look at the 3.1 spec, it says the 3.1 modem must support 258 megahertz to 1.218 gigahertz, but it says it may support 108, like DOCSIS 2.0 and DOCSIS 3.0. So we are seeing some customers saying, well, you know what, I'm going to put my OFDM block, my DOCSIS 3.1 downstream block, up at the high end because that's where I have open spectrum. But they might be doing some analog reclamation and have low-end frequencies that are open now, and might put the OFDM block down there at, say, 258 to 450, 192 megahertz block. So assuming they go all digital and there's no analog anymore, maybe that's where the spectrum opens up. So the question becomes, where is it better to put it? On the high end, the low end? And if you're cross-bonding with your single carrier QAMs, do they really need to be contiguous? Do you care? Could the OFDM blocks be down at 258 and the single carrier QAMs are up at 650? You know, is there a concern there? And I think, you know, that's kind of some of the things we're seeing in some of the results is we start in the high end, but some systems are looking to put it at the low end because power levels are better and better MER readings. I'm going to pass it back to Jason.
Yeah, I was going to say for their deployment too, I guess kind of like anybody, they initially deployed where they had some spectrum, and actually some of the initial spectrum was beyond a roll-off. They had a kind of a 750 plant that had been upgraded to 860, but they were actually running their frequencies all the way out to like 910 megahertz. So this one part of this graph here, are you seeing it?
Yes,
Yeah.
I see the graph.
Okay, so like part of this one here, we first deployed it, and these are even to your points of your subcarriers, they were running like 144 megahertz wide channel, and anything that was out here maybe above subcarrier 3000 was out into the roll-off above 860. And they certainly saw some degraded part there, but they were still able to run 1024 QAM out there in the roll-off. They just weren't able to run that at a higher order modulation.
So you pass it back to me?
Yep.
Leave that up. All right, so those graphs, as an RF guy, you might think of it like frequency versus amplitude, but it's not. That information is being grabbed from the cable modem. The cable modem reports MER readings on a subcarrier basis, so there might be 4,000 subcarriers there. We're getting the MER readings, running it through a Python script, and then we're graphing it out. So that's actually MER versus the subcarriers.
Oh, so the top graph is MER versus subcarriers.
Yes.
Yes. So don't be confused when you look at that and think that's the in-channel frequency response.
Right, now I understand how to interpret it.
More like the in-channel MER response.
Right.
So I'll go back to Jason now.
But what we would do then with this part of it would be, and the reason we were kind of for us, back to your point, you know, there's certainly things you want to measure. For our particular value, when we were first doing this testing, we were very interested in what those received MER values were per subcarrier so that we could start seeing, as we made changes to the configurations, what kind of impact would they have. And one of the biggest ones that we changed initially with these guys would be with some things around cyclic prefix. So the cyclic prefix makes the channel more robust to some of the micro reflections, etc. And on here, you could see that certainly there was roll off towards the end of that spectrum because that was, or we had lower received MER values towards the end of the spectrum, but that was just because that's the way the channel was, because it was into the roll off. As we saw the beginning part, though, we assumed that might have been more a factor of some micro reflections. So this is with the cyclic prefix of 192 samples. As we moved it to 512, and you could see at the beginning part of the spectrum, that cleaned that out and actually bumped the average receive MER up about 3 dB for that particular carrier.
Okay, let's hold on a second. I'd like to try to summarize this for people who may be listening to just the podcast only. So the first graph that we showed looked like there was about 3,000 subcarriers whose MER rolls off at the lower end of the subcarriers down to about 27 dB MER, and that ramps up to about maybe a little higher than 35 dB MER all the way across to the higher frequencies, and then it starts to roll off. Or you're saying that we're actually going higher in frequency than what the RF amplifier can support. So we're actually able to run an OFDM signal beyond the frequency range of what the amplifier can carry, and we're doing that at a relatively high MER, higher than 30 dB. Is that correct?
That's right, exactly.
And then the next slide that you went to, you made a change. I wasn't sure what the change that you did, but this change, we have 40 dB MER in frequency across the band, all the way out past the frequency with which the amplifier can carry for 3,000 subcarriers. It does drop a little bit at the very end to 35 dB MER, but this is still really good MER.
Right.
And so what change did you make that we have now really good MER out past the frequency with which the RF amplifier can change, higher than 35 dB MER?
Right. So on the OFDM channel itself, we have a setting for cyclic prefix. And the cyclic prefix on the first one was 192, which would be the minimum cyclic prefix. As you increase the cyclic prefix, you add a little bit of overhead so that the channel can't run as fast. But in this graph we have here, this graph is actually when we bump the cyclic prefix up to 512. It increases it so that this channel would be more robust against micro reflections. To be honest, whether that was actually happened or not, I don't know, but it was clear that we saw an increase in the receive MER performance on the lower subcarriers by bumping up that cyclic prefix.
Okay, so basically you learned that you can tweak the OFDM channel, so you trade off bandwidth to get really a massive improvement in MER so that you can run a higher order modulation, which would increase the amount of data that you can transmit through the pipe. Is that what you're telling me?
It's ironic. It's like you have some tweaks you could do, which is robustness versus speed, right? The trade-off.
But by doing that, you get more speed.
Yeah. And in the return, we end up with more speed because we can now support higher modulation schemes.
Right. I mean, it's almost counterintuitive. It's like, okay, I'm going to lose speed, and then by doing so, I'm going to get higher MER, which gives me more speed, which is totally cool.
But one of the things on this particular one too was this might have been I think it might have been like a 5 or 6 amp cascade. When we looked at some other modems that were at employees' homes that were closer, well, maybe they didn't see the same benefit for 512 cyclic prefix. Maybe they saw it for a lower value. One thing that was kind of interesting too. So originally they were in the middle, while they were doing this particular testing, they were in the middle of doing some analog reclamation. Once they completed that, well, then they no longer needed to keep this spectrum at the top, use the OFDM channel at the top of the spectrum. So this is the same location, but now they moved it down. I don't have what the frequencies were, but clearly it's down into the lower part, maybe somewhere around 400 megahertz in their plant. So now it's clearly within their guard bands, and you could see now where before that modem was able to run 2048, now this modem is able to run 4096 QAM because of the bump up in the signal noise ratio.
Right, now you're showing higher than 40 dB MER a whole way across the band, but you're showing a notch about a third of the way in. So why are you showing the notch in the middle, not quite the middle of the OFDM spectrum, but you're showing a notch there? What does that tell us?
For there, they still had an analog carrier that they were using for AGC, I assume. So they had to notch out around that so that they didn't interfere with that. So that's what you're seeing there.
So that's awesome. That's awesome that we can do that with DOCSIS 3.1 OFDM channels. They don't have to move their pilot. You're basically talking about the pilot for the AGC. We can just notch that right out around there and deliver DOCSIS 3.1 on the downstream.
Right. And one of the things that I also started seeing that this was so much cleaner than what we saw before. I was wondering that if we could maybe drop that cyclic prefix back down to 192, maybe we could gain that overhead back in that channel. But clearly not the case. So this is when I dropped that cyclic prefix back to 192. You could still see that there's still some rounding off or some lower values for those lower subcarriers.
Right. And so for our audio-only listeners, when we drop the cyclic prefix down, we're basically seeing that portions of the OFDM spectrum have dropped in MER all the way down to 30 dB MER in some places. In others, they're up at 40, but definitely we lost bandwidth, or we lost data throughput by dropping the cyclic prefix down. And I have a question. When you drop the cyclic prefix, are you doing this in the CMTS? Is this like a command line feature in the CMTS?
Yes, in the CMTS, we define an OFDM channel profile that has the parameters like whether we're going to run, what type of data profiles we're going to have. Obviously, we could have multiple data profiles, which is one of the benefits of DOCSIS 3.1. But in there, we also have these settings for things like cyclic prefix roll-off, whether we want 50 kilohertz spacing or 25 kilohertz spacing for the subcarriers. So that's a one command that we do in the CMTS, and then that pushes it out to all the cable modems on that downstream OFDM channel.
So this is kind of like part of modulation profile? Is that where this command goes?
It is, yep.
This is awesome. This is really cool stuff to see.
It almost looks like that rolling off or lower MER is almost like a group delay or a micro reflection.
Right.
You know what I mean? Like you're getting lower MER. Obviously, we don't have more noise there, but we're getting closer to where we have, in essence, almost like filters, exclusion bands, or potentially the AGC pilot is interfering maybe. But in this case, when we just change the cyclic prefix, it looks nice and flat in one case.
Yeah. So, but yeah, it's pretty. It was. Those are some of the things that we certainly gathered. A lot of stuff that it's difficult to see that in a lab environment where you don't have a live plant. Whereas when you start doing it in the plant, they were great enough to work with us and let us play around with some of these values. And it was part of the things that we included in the white paper that went along with our presentation for SCTE Cable Tech.
Right. So was there any other like amazingly awesome, cool discoveries that you guys noticed in the testing, like the cyclic prefix change that you did here?
I think that was probably one of the biggest ones that I didn't know about till we started testing. I would certainly think being able to support a higher order modulation was a pleasant surprise. I wasn't necessarily expecting that. So those are probably the big ones.
Okay.
Certainly some tuning that needs to be done still.
Very cool. Very cool. So, without anything else on the grass before we move on, because I'm kind of interested in like how licensing and everything works on this compared to what it was on the 10K platform and stuff.
Nope.
Because it's like it's easy to understand doing like single channel QAM licensing stuff, but when you do a whole OFDM channel, does that change?
I'm done. Sorry, I had it on mute.
Oh. No problem. I was asking you, I remember like on the 10K and RF Gateway 10, the way that licensing would be handled on a per line card basis. Is that going to be the same way on the DOCSIS 3.1 and CBR8 platform?
Yeah, I'm going to let Jeff comment on it.
Hey,
yeah,
Jeff.
fortunately the answer to that is a hard no. Yes, the UFA did associate the licenses directly with the hardware, whereas with the CBR8, we've moved to this new thing called smart licensing, where licenses are just aggregated and reported usage to the Cisco back end and kept track of there. So you can replace line cards, do line card failovers, etc., turn on features and QAMs without having to go through the hassle of upgrading hardware licenses.
So I actually see that as a benefit, right?
Oh yes, it's a big benefit. Yeah, much easier to deal with.
Good, excellent. I like that. Any updates on video encryption?
Or video in general?
So we, as of this past summer, we issued a release to support both power key and PME encryption for video on demand and switch digital. Well, actually, for video demand services, we also do support switch digital video and broadcast, pre-encrypted broadcast as well. We're just coming up with a release later this month. It'll have the first support for DVB encryption. DVB. Yep. Yeah.
All right. Excellent. Because I mean, video is becoming at least IP video is becoming a thing that a lot of customers are looking to do over CCAP devices. So, okay. Anything else on that?
Listen, John or Jason, you want to add?
No, I mean, I think the licensing being a pool of license It makes it much simpler, a lot simpler. 3.1, we also noticed that our own licensing on 3.1 is going to be in increments of 6 megahertz, but it's for the whole chassis. So you might turn on an OFDM block that's 144 megahertz wide on 8 cables. You have to add it all up, but it's not just 8 times the 144 divided by 6. That's how many license. We actually license on the usable spectrum of the 144. So Jason was talking about the roll-off or the cyclic prefix. We have this taper region, I think we're calling it now. So out of the 144 megahertz, really you might only be using 142 megahertz of usable subcarriers. You understand?
Yep.
Then you divide that by 6. Well, you add it all up with the whole box, divide by 6, and then we round it down to the lower integer of 6, and that's the number of licenses. So, for instance, a 192 megahertz block is the equivalent of 32 single carrier QAMs, right? It's equivalent spectrum.
Mm-hmm.
If you take 32 times 6, it's 192 megahertz. Well, it turns out on 192 megahertz with the guard band, and we do all the math, it turns out to be 30 license, I believe. 30 license or 31?
31.
It's 31.
Yeah.
Yeah, it's
but
like
as you add up more ports with that, then it might be less. Right?
Yeah. So, I mean, I just find that there might be a slight increase in the 3.1 license cost over 3.0, but then we're also rounding down, so I'm not paying for guard band. You understand what I'm saying? Like, even though it's 192 megahertz, you're actually paying for the usable spectrum, the usable subcarriers, which is kind of an interesting way to go about it. But I'm finding licensing being as a big pool is much simpler than how it used to be on the 10K and RFDW10.
So how would it work with a virtual CCAP device then with licensing? Because it's not really, well, there's hardware involved, right? There's physical ports, but it's like you said, it's almost like a server. Because
it's not released yet. My understanding, I think the way it will go would be, it would all be software, and even though the RF is hardware coming out of a node or whatever, you wouldn't be licensing RF. You'd be licensing the control of that RF. So you would have a license on the virtual server. You'd have a license on the CMTS controlling the QAMs coming out of the node. You wouldn't be charged for the RF being activated on the node. Do you understand? Make sense?
Yeah, it makes sense. I want a DOCSIS 3.1 CMTS, so I want to download it.
We'll give you the software version.
So, all right, John. So, what keeps you up at night with DOCSIS and talking to your customers?
All right, I'm switching over back to mine. You should be able to see me now.
Yep.
Can you see me now? So, one of the biggest ones I've been coming up with lately was monitoring. Operational monitoring on the CMTS, meaning are cable modems doing what you think they're supposed to be doing? You could have a 3.0 modem that should say W online, but it's actually online, which is not a good sign. It's not a good state. It's basically operating as a DOCSIS 2.0 modem. So if that modem is a paying customer for 100 meg service and he's registered as a 2.0 modem, the most he's going to get is 30 meg. And if he gets to 30 meg, he's going to starve out everybody else on that one downstream because he only supports one downstream. And if that's the case, then load balance kicks in. So this one modem that didn't register properly is also affecting other people and affecting load balancing. So it's like a domino effect. So to me, we need to be more proactive in monitoring our CMTS for proper operation, flags, alarms, SNMP, proactive maintenance, all that stuff. So I'm seeing, I have another example for you. I have modems that say /UB, meaning upstream bonding. And then I do a showcam modem wideband channel command, and I notice they're saying 8x1. Well, 8x1 is not a good state. So by default, in our CMTS, we have single channel bonding groups on the upstream. And we do it on purpose because scheduled flows like voice don't get bonded on the upstream. To guarantee jitter and latency, we push them on the single channel upstream bonding group. So a 3.0 EMTA, if it has a voice call, it'll go up a single channel bonding group. So you could have a modem that says UB, upstream bonding, and you assume it's doing 4-channel upstream bonding, and it's not. It could be doing single channel. So unless you know to look for that, you might not have any alarms pop up, and modems could be 8x1 mode and you don't even know it. And if it's 8x1 mode, then you're not going to get the speed on the upstream you think you're going to get. You're probably only going to get like 5 meg. It still says UB, so you think it's doing upstream bonding, and it sort of is, but it's not doing 4-channel upstream bonding. So these are the type of things that kind of I've been tracking lately and trying to help customers understand. Do you have a denial of service attack on your CMTS? Is it taking a lot longer for devices to register? Are modems even bonding in 24-channel or is it an 8-channel? If you have 32-channel bonded modems out there, but you don't make a 32-channel bonding group, they should lock onto the 24-channel bonding group. If not, you should understand why. So I'm seeing cases where devices are not registering in the proper bonding groups, or load balancing is not configured correctly, and then the modem gets tagged with a certain tag or parameter and gets pushed into a load balance group, which then restricts it from doing the proper bonding. So there's a lot of little tweaks that you can do. You know, the old saying, I give you enough rope to hang yourself. Well, that's what's happening is there's a lot of functionality in DOCSIS. There's a lot of features and tweaks. And I like those features and tweaks for power users, people that know what's going on. So you want your defaults to be idiot-proof. Don't want to use that term, but you want to make the defaults that you can plug and play, but then people will start manipulating some settings or not understanding the defaults. So then we come up with best practices. So that's what Jason and I and Jeff Forehand and Jeff Riddell, we all end up being kind of liaison with the customer and saying, all right, here's what we see in other customer sites. Here's what we see in the cable plant. Here's the pros and cons to tweaking these different things. I can't really tell people exactly what to do, but I like to just tell them, here are the pros and cons. Like Jason just mentioned, the cyclic prefix. That's something new that's happening with DOCSIS 3.1. What are the pros and cons? Well, you can increase it, give you better robustness to maybe microreflections, but you're going to lose some speed. But on the flip side of that, getting better MER might allow you to go to higher modulation, which gets you speed back. So, you know, there's pros and cons to everything we do.
Right.
So that's what's kind of been keeping me up, is explaining to people how to monitor the CMTS for proper operation, modems that are not in the right mode, not doing the correct bonding, modems in partial mode, how load balancing is working. It's all those little things.
So is that what some of the testing you're doing in RTP this week?
Yeah, I mean, trying to, Jason mentioned, we have our own little spreadsheet to calculate upstream and downstream speed with different settings for 3.1. And it's like, how do you prove your spreadsheet is right unless you actually do real testing? And the odd thing about testing, you know, when we do speed testing, are you doing UDP or TCP testing? We want to do UDP testing, so it's individual downstream or upstream, not downstream testing is affecting upstream. You understand? Like with TCP, downstream traffic makes upstream acknowledgments, and we don't want to do that. So we make sure our test equipment can do UDP. We do with the biggest frames possible, 15, 18, or 1500 byte Ethernet frames. We tweak a few settings to see if we can get better speed, but when you do individual modem testing, that might not be true to a real cable plant. Normally in a cable plant, you're going to have many modems doing maybe 10 meg, 100 meg, a gig. But when you try to push line rate to a single modem, then things get a little sketchy. And that's what we're trying to figure out is, you know, what is, if I start doing DOCSIS 3.1 upstream testing, what is this aggregate pipe worth? Well, with a single modem, what if I only get 200 meg, but my calculator says 300 meg? Well, maybe it's because I'm hitting a single modem limitation. So I throw 2 or 3 modems on and do 100 meg a piece, and now I'm hitting, say, 285, and my calculator says 300. I'm like, okay, I'm pretty close. So those are the type of things we're doing, is trying to prove out how much DOCSIS 3.1 is really worth as far as speed goes. I'm very confident with DOCSIS 2.0 and 3.0. I know an ATDMA is worth about 27 megabits per second. 8-channel upstream bonding, I can get about 216. We've proved that out. We've tested it. We know the mini slot allocations. We tweak things. We might do it over 2 or 3 modems, but it's about 216. With 3.1, you know, those questions are still coming up, is what is it really worth? How many subcarriers are really active? How much overhead for the pilots? How much overhead for the roll-off? How much overhead, blah, blah, blah. You know, there's a lot of what-ifs and gotchas and the tweaks. That's what we're trying to figure out.
Right.
And we didn't even get to like how robust it is to different noise. Like we haven't even got to that point where we want to inject noise in the upstream. On the downstream, Jason's been doing some testing on the downstream, which I think in one of the last meetings we had, I thought was interesting is interleaving is not just time-based interleaving, it's frequency interleaving as well. And OFDM, I think, is inherently better for microreflections and group delay and stuff like that because of subcarriers or whatnot. Did you just whatnot that? I just yada, yada, yada.
No,
the whatnot. So we found that the interleaving is not just time-based, but it's frequency-based. When we injected noise, and we inject it in the form of a QAM carrier, and Jason could probably show one of his graphs. I'll have him pull it up, where he injected 6 QAM carriers underneath, like 6 single carrier QAMs underneath the OFDM block, and it basically, because MER readings, it looks like QAMs going down from the top side because the MERs drop, but you can see where the QAMs are. So instead of the QAMs coming up underneath like a frequency plot, it's the MER plot, so it actually lower MER. And I'll have him pull up the graph. What we found was the MER across the whole spectrum still stayed pretty good, even though we know the CNR was much worse where the ingress was. And we believe it's because of the interleaving of time and frequency. Kind of like you're spreading the pain out across many more subcarriers. You understand? Like even though I inject noise at this one frequency, because of the interleaving, even though the CNR is pretty bad, the SNR was still reading relatively good, and my profile management was still allowing me to do, say, 1K, 2K, or 4K QAM, even on that spectrum I know had a low CNR.
Yeah, so you're basically just saying the OFDM is much more robust to the impairment that's underneath it.
So let's go over to Jason's and look at his real quick.
Okay, so we have this plot up.
Yeah. So if you look at the top graph, that would be 1, 2, 3, 4, 5 QAMs injected underneath, and if you transpose it on the top, like coming down, that's showing lower MERs where the QAMs are.
And this is a 90 megahertz wide channel, this particular example.
So what's interesting on this graph, if I interpret it correctly, is it looks like where the MER is really low, you're saying the MER is about 30 dB MER, exactly where the SC QAM channels are underneath the OFDM channels. And then the MER goes up to like 40 dB where there is no SC QAM channels. Is that correct?
Correct.
That's right, yep.
And even where you see the spikes going up, that would be in between the QAM interference. So the MERs are actually good there.
Right. So it's amazing that you can put an SC QAM channel underneath an OFDM channel and still get 30 dB MER in on the OFDM.
Well, no, I'm saying no. It's showing 30 there, but the average across the whole channel is still showing close to 37. Kind of like I guess that's the average for the whole thing.
It is, yeah.
But we had no uncorrectable effect, and we were still running 4K QAM, right?
This was running actually. This one here, if you're looking at the graphs, the graph right before, we had a 30 dB pad on that interfering signals. We were still running completely clean 4096 QAM. We actually forced the modulation to stay at 4096 QAM and not drop down to a lower data profile. And we still ran through here, certainly high correctable FEC errors, but no uncorrectable FEC errors up until we got to this next point where when we went to 29 dB pad, we started seeing an occasional uncorrectable FEC error rather.
Right.
So my point, Brady, was we even tested with speed to make sure like the OFDM block was not like using subcarriers and not using the subcarriers where the ingress was. So we knew the traffic was on all the subcarriers, even where you had a 30 dB SNR. So that 30 dB SNR where the ingress was still carrying, in essence, 4096 QAM traffic. So to say that you could work at 30 dB seems unheard of.
Right.
Yeah, I think we're going to see a lot more of these sort of testimonials like this, where we're seeing an OFDM signal working in really amazingly harsh conditions, but we're still getting very high MER at very high orders of modulation and really good data throughput. Just because OFDM is so resilient to impairments, is like we are demonstrating in this screen.
Yeah, and I think what part of this testing was too is obviously we have multiple data profiles that we could send out and transmit to modems. And so what we do from the CMTS standpoint, we poll the cable modem to determine what would be the ideal modulation to send out to this cable modem. And we had to do some adjusting on that because it was probably a little bit conservative at the beginning that in this particular case, we would have been recommending to run 256 QAM modulation to this cable modem when actually it was still able to support 4096 QAM. So some of this testing was to figure out what was the right tweaks that we would need to do for those algorithms to pick that profile.
Right. No, I mean, the great news here is that so many of us were like, how are our plants ever going to support 4096 QAM or even 1024 QAM? And what we're seeing now is it not only can we do it, but we can do it in many places. We're finding tweaks that we can do to make it do it even better. And I think we're just going to continue to do this successfully. DOCSIS 3.1 is working really, really well. And we're just going to continue to make it perform even better as we learn how to optimize it over time.
Yeah, what I see exciting right now is we're working on this graceful profile management where, we talked about, we're looking at 1 or 2 modems, what Jason is showing, but in a real plant, you have some modems off the node, some modems off the 5th amp cascade, so they're obviously going to have worse MERs, and some modems are going to have MER that's bad because of a suck out or just noise or whatever. So the profile management is getting more intelligent even from our side, from the CMTS, where we could, send you a certain profile, send Jason a different profile, and send me a different profile, all on the reporting of our individual MERs for every subcarrier. So we could have different profiles already made up. Could be mixed profiles, could be a 4K, a 1K, a 256, whatever. Based on what you report back, I might assign you to that new profile on the fly. Now, what I found out was the modems have to support, I think, 4 data profiles.
Yep.
But our CMTS supports like 5 data profiles. And so if the modem says, all right, I have 4 data profiles logged into my modem itself already, and it says I have poor MER, so I'm going to drop from profile 4 to profile 3, it'll do it, and maybe I lose 1 ping or whatever, but it doesn't go offline, and it automatically changes to a new downstream profile. So that's kind of cool. The only thing I saw is a little bit different as far as layer 3 drops was if the modem pulls up the 4 profiles, 1, 2, 3, 4, but then we want to push it to profile 5, that modem has to pull that new 5 profile in because it can only store 4 at a time. And then we end up using a DBC, dynamic bonding change, to get that new profile to it. So if that happens, then we might lose, say, 3, 4, 5 seconds of ping. Because when you do a DBC, you're going to end up probably rearranging the upstream, pre-EQ, whatever, and you end up losing layer 3 ping, maybe 2, 3, 4, 5 seconds. But the modem stays online, it gets a new profile, he's ready to roll, the downstream's going again. So, I mean, this automated approach of changing the profiles without having to reboot is pretty key. I mean, it's one of those things I find that's going to make it more operational, like a real live solution. Before we said, we can put DOCSIS 3.1 out there, but what if something's wrong with the OFDM channel? What if something's wrong with the single carrier QAMs? What if I have noise? What? Now you have a customer paying more money for higher speed, and it wouldn't work at all. But now with the profile management, we can monitor the modem. The modem's telling us what's going on, and we can push it to a new profile. And the fact that I wanted Jason to talk about the PLC. Some of the testing we're doing now is with this PLC, the physical link channel.
Yep, physical link channel. Physical link channel.
We know it's 16 QAM. You can put it in any spectrum you want where you think it's clean for your plant. We wanted to see what happens if we knock that out. Well, at 16 QAM, it's going to take a lot to knock it out. So Jason, that was one of the tests we were doing while we're here. Jason was messing around with ingress under the PLC. So I'm going to go back to him and let him talk about the PLC.
Yeah, one of the things that we weren't quite sure about, and it actually, all this testing we originally did around a lot of the noise, we intentionally avoided the PLC because we didn't want to knock down the whole OFDM channel if it was more susceptible to some noise. So this round of testing, we also were kind of curious to see the physical layer link channel itself is only 400 kilohertz, but it occupies, well, there's 6 megahertz of spectrum around it. So we now had a single carrier QAM, 6 megahertz wide, that we turned up right on the PLC spectrum. And we kind of wanted to see how far we could go before we actually would lose the PLC itself. And in this particular one, you could see it looks like and again, this is all taking receive MER values back from the modem and then graphing it out. And that top graph, where everyone else is more closer to around 40 dB for receive MER value, we're down below 15, and we're still running the PLC without any problems.
And Brady, you know as well as I, on the upstream 16 QAM, we always would quote, say 18 dB as a cutoff point.
Yeah,
now with the
18
LDPC,
that we would expect 16 QAM, that those modems to be offline. But you're saying these modems are still online with like below 15 dB MER on the PLC.
That's right.
How is that
but
possible?
This was right. Once we went back to this particular one, that when we moved it to 10 dB, well then the PLC we lost a lot.
So what was the last? What was last?
And that one was 12.
So just a 2 dB. So it's like the digital cliff effect, right?
Oh yeah.
We found out where that cliff was. So we changed the padding to make the ingress higher by 2 dB, and then we end up losing the PLC.
Yeah. So.
But the break point seems to be a lot lower than you would expect.
That's right, and that's kind of what we were seeing. Obviously, in a real world, you wouldn't want to get to that point with your PLC, but it is good to know that that can also tolerate quite a bit of noise.
Yeah, I mean, to your point, though, that has got to be an amazing amount of noise that you would have to have in the real plant in order to knock out a PLC channel, to knock your plant down to the point of like 13, 12 dB, whatever you're saying that is of MER. That's an amazing amount of noise.
Yeah, I mean, I was afraid, some people are putting their OFDM block up at the high end, and if the PLC happens to be right at the same frequency as LTE, would LTE end up knocking it out? But being 16 QAM and seeing some of these results, maybe that's not as big of a concern as I thought. I mean, I would still avoid it. Ounce prevents is worth a pound of cure. I would still avoid LTE and off-air digital broadcast, but knowing that the breakpoint is so low,
there would have to be a lot of LTE.
Yeah. I mean, when 3.1 came out, I really thought it was an undersight by our own guys, Cable Labs and the MSOs. Like right now on 3.0, you have a primary downstream, one. I thought with 3.1, we would come up with an idea of like 2 primaries, 2 PLCs, like a secondary primary, like a backup. But this is so robust that why would I lose more speed by making another PLC, right? Because you're going to lose more speed because you're going to have more unused subcarriers because it's a PLC.
Yeah, I'm really, really surprised by that. I'm impressed by how resilient that is. That's awesome. It's a good study. So what else? What else is, a lot of good information. What's coming up for you guys now?
Jeff stepped out, but I know Jeff is going to be going to Berlin, I believe, in February for Cisco Live. There's a Cisco Live out in Berlin. Jason was at the SCTE Expo. Ron was out there. Jeff was out there. Jeff Forehand. So we did a lot of stuff. You were out there, obviously. I think Brady, you even introduced. Why don't you tell us about that transponder thingy you were working on?
Yeah, so we had worked with Hytron. They have a product called a CMSO2. And so that's a cable modem with 3 extra ports on it that you can switch between with an RF switch. And it gets mounted into a fiber node or an RF amplifier. So we were demoing that at Cable Tech Expo. And the ideal place for it, you put it in amplifiers. It comes online as a cable modem. You don't need any extra head-end equipment, and now it's a remote transponder, but it gives you the ability to do full band capture both on the upstream and the downstream of any test point in an amplifier or fiber node.
How does it wire in?
So it uses small little micro, I forget the name. But
SMB?
Yeah, they're MCX on the device side, and then just F connectors that go into the regular test points in the node or amplifier. And it can even go into a line extender if you want. It gets 24-volt power off of the power supply in the amplifier or nodes. So it's powered all internally, and it's rated to industrial grade temperatures. So it goes from -40 to +60 degrees Celsius.
So the RF switch is controllable via software, SNMP or
SNMP, yes.
So almost like the old Wink switches or addressable tap or something. You could control it and turn certain legs on and off, or look at individual legs.
You can look at each individual leg. I mean, both the cable modem, you can look at that, or you can look. The cable modem has a diplex filter, which gives you some space that you miss, but the other ports on it have no diplex filter on it. So you can see all the way down from 5 megahertz up to 1 gigahertz on the test point in the amplifier. So it's a really nice way to, if you have 3 outputs on a trunk, for example, and you have a lot of return path noise coming back into that trunk amplifier, normally you have to go out to that trunk amplifier and start pulling pads to see which leg the noise is coming from on a trunk. With this, you can just toggle between each return on that trunk and very quickly see, okay, it's coming on a trunk leg or one of the bridger port legs of the trunk amplifier.
Can you go below 5 megahertz?
Not right now. We're talking about the ability to go below 5 megahertz, but I
basically it's the DOCSIS chipset, right?
Yes.
Like modem.
Yeah. So I think you can't go below right now just because of a software limitations, but I think eventually we'll be able to overcome that.
Now, what if I want to put it in a node that has 4 outputs? I see why you did 3, because amplifiers typically have an input and 3 outputs. But what if it's a node that has fiber in but has 4 outputs?
You'd have to combine 2 of those outputs, because actually one could be on the cable modem side. So you would have the diplex filter on the cable modem side, and then you would have 3 that would not have the diplex filter on the cable modem side.
Okay.
So you could actually monitor 4 ports at one time.
Okay. And so very small form factor?
Yeah, it's super small. Like I said, it even has a mounting kit for inside a line extender. So they make mounting kits for a bunch of different vendor equipment.
And so does it show up as a cable modem on my CMTS? Yeah,
it's going to have a MAC address and an IP address. We did a custom development for our PNM application, so that when it shows up, we automatically detect it, and we have the ports mapped on it, so you can switch between the ports and look at them individually. So that's automatically integrated with our PNM application.
How do you control the upstream downstream level? Just a pencil pad or something?
Yeah, so
they're in line with the F connector.
In the software, there are it gives you the ability to control and set the attenuation. So, like if you're on a 20 dB test point, you can control the attenuator and set that reference point.
I'd still want that modem to maybe transmit at 45 on the upstream.
Oh yeah. So the modem's going to do all of it's going to register with the CMTS and transmit at whatever level it needs to get back to the CMTS.
That's what I'm getting at is if it's only through a 20 dB test point and it's right there at the reverse amplifier or whatever, it might only be transmitting 23. So how do I make it transmit 45? Are you saying that software control to make it transmit 45?
No, I mean, at that point, you would have to put if you want it to transmit at a higher level, you're going to need to put a pad on it. But if you're right at the return transmitter, SNR is probably not going to be a problem.
Yeah, well, my reasoning for having modems transmit hotter is if that device, just like I've talked about this before, if you have devices transmitting like 35 dBmV, 20 dBmV, if they go crazy and they start transmitting 60, they go in la-la land and screw everybody else up. So I'd rather have a modem operate properly close to 45. That way, if it does ramp up higher, it's really not going to be that much higher.
Right. I understand what you're saying.
All right. So in the downstream, the same deal, right? If it's right there off a test point and it's a high output amplifier, 60 dBmV, and it's 20 dB down test point, you're hitting that thing with 40.
Yeah.
Right?
Yeah. So there's attenuators in it that you can switch in.
For downstream.
Mm-hmm. Yes.
Okay. All right. Very good.
All right. So guys, we are at the top of the hour. I want to thank you all. This was a very informative session. Great information on DOCSIS 3.1. Thanks for all the information. Appreciate you taking the time to be here. Any final thoughts?
Yeah, appreciate y'all letting me hang around. I appreciate you let me tag along with you and John. Brady, Jeff says the same.
All right. Thanks, guys. Take care. Have a good Thanksgiving, and
We're gonna photoball. Here we go. We're photoball.
Cool. See you.
All right. See you later.
see ya.